Welcome to the KNIGHTARISEYT.
Today, we are embarking on what is quite literally the most epic journey possible. We are going to reverse engineer reality itself. We're going to trace the entire history of the universe, stepping all the way back to its absolute origin. We'll be dissecting the math, the quantum physics, and the truly mind-bending phenomena that built the cosmos we live in today. So, get comfortable, get focused, and let's unravel the greatest mystery of all time together. To start us off, I want you to think about a brilliant riddle posed by the ancient Greek philosopher 𝐂𝐻𝐋𝐋𝐁. He asked, "If I am at the edge of the universe, can I stretch out my hand or my staff? If not, what is stopping it? And if I can, there must be space beyond, and so on without limit." Using this exact logic, the Greeks concluded that the universe simply must be infinite and have no edge. It's a beautiful thought experiment, right? But is it actually true? Well, modern cosmology gives us a completely different and frankly much more fascinating answer. The idea of a static, eternal, unchanging universe is a total illusion. Our universe is evolving. It is expanding. So while it might not have a physical wall or edge in space that you can just reach out and touch, it absolutely has an edge in time. It had a definitive beginning. Here is how we are going to break down this journey today. First, the expanding universe. Then, rewinding to the singularity. After that, the first 3 minutes, followed by the cosmic microwave background, and finally, we'll map out the cosmological standard model. Let's start with Section 1, the expanding universe and discovering the edge of time. Let's look at the hard, empirical evidence that completely shattered the illusion of a static cosmos. Up until the 1920s, scientists, including Einstein at first, generally believed the universe was static. But then, in 1924, Edwin Hubble started measuring the distances to remote celestial objects, and he found something absolutely shocking. The light from distant galaxies was redshifted. This cosmological redshift meant that these galaxies were physically moving away from each other. And not just that, the further away a galaxy was, the faster it was receding from us. Now, you might hear that and immediately think, wait a second, if everything is flying away from us, doesn't that mean we are exactly in the center of the universe? Well, no. To understand why, we have to look at the cosmological principle. This principle assumes the universe looks roughly the same to all observers, anywhere. Think of space like the surface of an expanding balloon. If you take a marker, draw a bunch of dots on a balloon, and blow it up, every single dot moves away from every other dot. Space itself is what's stretching. There is no central dot. So how do we translate that mind-bending observation into actual math? We use Hubble's law. This defines the direct proportionality between a galaxy's physical distance and its velocity. And the engine driving this equation is the Hubble constant, known as h0, which sits at approximately 70 kilometers per second per megaparsec. Let's really think about that math for a second. For every megaparsec, which is roughly 3.26 million light years of distance, a galaxy's recession speed increases by 70 kilometers every single second. This equation is the literal bedrock of observational cosmology. Moving into Section 2, rewinding to the singularity, our journey to the very beginning of space-time. If space is currently expanding like that balloon, what happens if we physically run the cosmological clock backwards? Things get denser and hotter until we eventually hit a mathematical wall about 13.8 billion years ago. We call this the Planck epoch. Here we reach the Big Bang singularity. Now, you need to understand, this isn't just a really dense star. It is a point of infinite density and gravity where the very concepts of space and time completely break down. General relativity and quantum mechanics, they just stop working here. Then, at 10 to the power of -32 seconds, the universe undergoes a period of violent, unimaginably rapid expansion called cosmic inflation, setting the stage for everything that follows. To truly grasp this early, chaotic universe conceptually, cosmologists rely on some incredibly heavy mathematics, specifically the Friedmann equation. Derived directly from Einstein's field equations of general relativity, the Friedmann equation allows us to calculate the scale factor of the universe over time. It flawlessly balances the energy distribution of radiation, hot gases, matter, and the cosmological constant to describe this incredibly unstable, expanding fireball. It is without a doubt the mathematical heartbeat of the Big Bang Theory. Let's jump into Section 3, the first 3 minutes, and see how the elements of matter were actually forged. Let's look at how this seething ball of energy built the physical matter we interact with today. Imagine the universe when it is just one single microsecond old. It was what we call a quark soup, a chaotic, glowing plasma of quarks, gluons, electrons, and antiparticles. As the universe expanded and cooled to a mere trillion degrees, quarks could finally bind together to form protons and neutrons. But there was an epic war happening. Particles and antiparticles were constantly colliding and instantly annihilating each other into pure radiation. But for reasons physicists are still desperately trying to fully understand, there was a tiny imbalance. For every 30 million antiparticles, there were 30 million and one regular particles. That tiny leftover fraction of surviving particles, that's what makes up all the matter in our universe today.
So exactly how did those surviving protons and neutrons start to build actual elements? This is a process called Big Bang nucleosynthesis. When the universe was around 1 second old, it cooled down to about 10 billion degrees. Now, at this specific temperature, the strong nuclear force finally became effective enough to allow protons and neutrons to actually stick together without being instantly blasted apart by high-energy photons. A proton and a neutron fused together, creating the universe's very first atomic nucleus, deuterium, which is a heavy isotope of hydrogen.
And that first fusion kicked off a massive, rapid cosmic chain reaction. Deuterium nuclei began fusing to create helium-3 and then helium-4. This incredibly intense, universe-wide period of nuclear fusion lasted roughly until the universe was exactly 3 minutes old. By that 3-minute mark, the universe had simply expanded and cooled too much for nuclear fusion to continue. The result of those 3 minutes? A universe made of about 90% hydrogen, roughly 10% helium, and just tiny trace amounts of lithium. The foundational chemistry of the entire cosmos was locked in right then and there.
But here is a number that should absolutely stun you: 4%. Cosmologists can measure the abundance of these early elements in pristine, ancient gas clouds to calculate the total baryon density, which is the density of all ordinary, normal matter. And the math unequivocally tells us that all the hydrogen, all the helium, every star, every planet, your body, my body, all of it combined makes up a mere 4% of the entire universe.
This brings us to Section 4, the cosmic microwave background, the echo of the fireball. Okay, so if ordinary matter is only 4%, how do you know our Big Bang model is actually correct? Let's fast forward the cosmic clock from that 3-minute mark to about 300,000 years later. For all that time, the universe was a dense, incredibly glowing fog of radiation and unbound particles. Light literally could not travel freely. It just constantly bounced off free-floating electrons. But eventually, the universe expanded and cooled to about 3,000 degrees, triggering an event called recombination. Electrons finally slowed down enough to be captured by atomic nuclei, forming the first stable, neutral atoms. Suddenly, the fog lifted. Light was finally free to travel unhindered across the cosmos. And the crazy part? We can measure this ancient, stretched-out light today. We call it the cosmic microwave background, or the CMB. Now, we've mapped the CMB with exquisite precision, and when you look at it, it isn't perfectly uniform. It contains these tiny, minuscule temperature variations, known as anisotrophies. So, what are these? They are the direct result of quantum fluctuations. During that initial fraction of a second of cosmic inflation we talked about, random subatomic quantum variations were stretched to massive, macroscopic scales. These microscopic ripples in density acted as the fundamental gravitational seeds of the universe. In the areas where the early plasma was just a tiny bit denser, gravity began to pull more matter in. This is literally the origin story of every single galaxy cluster in existence. Let's pull this all together in Section 5, the Cosmological Standard Model, covering dark matter, dark energy, and the cosmic web. We have traced the matter we can actually see, but now we have to confront the unseen forces that dominate our modern understanding of physics, known as the Lambda-CDM model. Baryonic matter is just that 4%. The vast majority of the rest is totally dark. We have cold dark matter, which consists of unseen particles with small random velocities. This provides the invisible, massive gravitational scaffolding that actually holds our galaxies together. And then, there is lambda, the cosmological constant, dark energy. We need to look much closer at dark energy because it is truly bizarre and frankly counterintuitive. As our universe evolves, it enters what physicists call a late-stage de Sitter expansion. It becomes entirely dominated by vacuum energy. This means that empty space itself, the actual vacuum, has an intrinsic energy density. So instead of the gravity from all the matter slowing the universe's expansion down over time like you would expect, this cosmological constant, this dark energy, acts as a powerful repulsive force. It is accelerating galaxies apart faster and faster every single day.
Now, to test if this incredibly complex Lambda-CDM model actually works, cosmologists don't just rely on telescope observations anymore. They literally build the universe inside supercomputers. Using immense computational power, they run what are called n-body simulations. They program in the cold dark matter, the repulsive dark energy, and those exact initial quantum fluctuations we see imprinted in the CMB. Then, they hit play and let the simulation propagate over 13.8 billion years to see if the computer's universe matches the reality we observe in our telescopes today. And the results of those supercomputer simulations? They perfectly match reality. Behold, the cosmic web. Over billions of years, the gravity of dark matter has pulled ordinary matter into these vast, glowing filaments of galaxies, leaving immense, dark, empty voids in between them. This structure is mind-bogglingly huge, ranging from objects tens of thousands of parsecs wide to the absolute largest physical scales of the known universe. It is the breathtaking culmination of 13.8 billion years of cosmic evolution, perfectly predicted by the math and physics we've discussed today. We have reverse-engineered the cosmos. We started at the Singularity, moved through the explosive first 3 minutes of nucleosynthesis, caught the echo of the CMB, and mapped the modern cosmic web. But I want to leave you with one final, deeply provocative thought. If dark energy is real, and the vacuum energy of space continues to dominate and accelerate the expansion of the universe indefinitely, what is the ultimate fate of all this? Will the cosmic web simply stretch and stretch until all the stars burn out and every galaxy fades away into an eternally expanding, freezing, dark void? It is a chilling yet incredibly beautiful mystery that cosmologists are still striving to answer. Thank you so much for joining me on this deep dive. Keep questioning everything, keep looking up, and I'll catch you in the next explainer.